Okay, so I'm going to go through the examples I set you for the first lecture as practice of index notation. And in each case, we're going to assume that there's going to be 3 dimensions. So that's going to be I can be equal to 1, 2, or 3. And this can, this can correspond to x1, x2, x3. So you can think of this as x, y, and z. Okay. Okay, so we take the first example. And the important thing is always to look at the number of free indices. This only has 1 free index. Here, so it's a vector. And if we write that out, we get the following. So here we have expanded this in our 3 dimensions, I, j, and k. And we have first for 1, then for 2, and then for 3. So this is the gradient in each spatial direction of the scalar quantity phi. Note that for completeness, I, j, and k correspond to your 1, 2, and 3 directions. These are your unit vectors. Okay, so let's look at the second one. Okay, so let's look at the next one. So here we have 1 repeated indices. We have I appearing twice. And when you have a repeated index, then you sum over that index. So this becomes du1 dx1 plus du2 dx2 plus du3 dx3. And because it's a repeated index, it equals a scalar quantity. Okay, we're going to look at the next one now. This one's a little bit more complicated because it features this cyclic operator. And as I said in the lecture, the cyclic operator, epsilon ijk, takes -1, 0, or 1 depending on the order of the indices. So we're going to define that now as follows. So if I, j, k are decreasing, so that you have epsilon 3, 2, 1, so I is equal to 3, j is equal to 2, k is equal to 1, or 2, 1, 3, or 1, 2, 1, 3, 2, and you can wrap around, you see, as long as it's continuously decreasing, then you take -1. Then, similarly, it takes a value of 1 if I, j, k are increasing. So if it's epsilon 1, 2, 3, 2, 3, 1, or 3, 1, 2. And finally, it takes a value of 0 if it doesn't fit into any of the above. Okay, so let's apply that now to this expansion. Now we can see that there are 2 indices, j and k, which are repeated, and 1 index, I, which is free. So the j's and k's are going to be summed up, and we're going to be left with a quantity which has rank 1, so it's going to be a vector. Okay, and so in order to work out one of these expressions, the first step is to write it all out in full, substituting the summations I equals 1, j equals 2, and k equals 3. Okay, so at this point, we've now expanded each of the terms, so we have 9 terms where we have summed together the values of j and k. So just to show you how that works, so In this case, we've had j is equal to 1, k is equal to 1, which is why we have 1, 1 here and 1, 1 here. In this one, we have j is equal to 1, k is equal to 2, 1, 2, and then because j is 1 and k is 2 here, and so on. For 1, 3, 2, 1, 2, 2, 2, 3, and 3, 1, 3, 2, 3, 3. So, what we're left with is a vector still. So the only free index in each of these terms is I, and they're all summed together. Now, we need to find what this vector would look like for 3 dimensions. And immediately we can see that because this cyclic quantity is 0, if it's not decreasing or increasing, then whenever there's a repeated index, 1, 1, 2, 2, 3, 3, this is going to be 0. So our first step would be to put this to 0. Now with the remaining 6 terms, we need to look at the cases when they're also not 0. And for the case where I is equal to 1, you'll have 1, 1, 2. So this will be 0, this will be 0 because of the 1, and this will be 0. This will be positive, this will be 0, and this will be negative. In the case where I is equal to 2, you will have this one being 0, this one will be negative, this one will be 0, this one will be 0, this one will be positive, and this one will be 0. And finally, for the case where I is equal to 3, this one will be positive, this one will be 0, this one will be negative, and this one, and this one would all be 0, because you would have then a repeated index of 3, 2, 3, 3, 3, 1, and 3, 3, 2. So you can see that it greatly simplifies from that expression, and then it can be summarized as follows. So, for I, you have x du3 over dx2, which is this term, positive, minus du2 over dx3, times in the direction I. In the direction j, you have u1 dx3 minus u3 dx1. In the direction k, you have u2 over x1 minus du1 over dx2. And this is the final answer. You'll recognise it, I'm sure. Okay, now we can move on to the next one. So this you will come to know as the Boussinesq hypothesis, and it has this special character or special term dij. This is a lot more simple. Effectively, dij is equal to 1 if I is equal to j, or otherwise it's 0. Okay, so again, we note that there is no repeated index here, and this, each term, has 2 free indices, I and j. So, 2 free indices, therefore it's a tensor. And this can be expanded like this. So, when I and j are equal to 1, in the first term, you have 2 nu t s11 minus 2/3 k, because dij is 1. In the case here, where I is 2 and j is 1, you have 2 nu t s21, and you have this is equal to 0 because I is not equal to j, and so on. Only on the diagonal terms do you have this minus 2/3 k, and this is because of when you're on the diagonal terms you have I is equal to j. So then the final term here we can see that we have two repeated indices, j, and one free index. So this is going to be a vector in I, and you sum over j. So the first step is to write it down to sum over j, 1, 2 and 3, like so. And you see you have j1 plus 2 and 3, and you still have the free index in I. And then you would then expand this as a vector. So this is what it would look like in the I direction, and also in the j direction and the k direction. And these are actually terms of the Navier-Stokes equations, both in the x, y and z directions. Okay, and that's it.